untitled circle before entering into your revised syllabus. In the revised syllabus, everything is there. What is in your previous syllabus? No topic is deleted from this chapter. So, before entering into the chapter, I want to tell you some basic concepts related to your standard 9. Go through it, recap or remind or remember your concepts of standard 9. First, the perpendicular drawn from center of a circle to any of its chord bisects the chord. Number 2, equal chords of a circle subtend equal angles at the center, or if two chords subtend equal angles at the center, then they are equal with each other. Then third one, throw three non-collinear points. Through three non-collinear points, we can draw only one circle. Then comes to the angle subtended by the arc at the center. The angle subtended by any arc or chord at the center is twice the angle subtended by the same arc on the remaining part of the circle. Then angles on a semicircle is always 90 degree. Then if a quadrilateral is a cyclic quadrilateral, then the sum of either pair of opposite angles is equal to 180 degree. These are the basic concepts related to your standard 9 syllabus. Now we will enter into the 10th syllabus. So the first concept is the position of points with respect to a circle. We know that when we draw a circle, the plane is divided into three different parts. One is called the exterior of the circle, other is called interior of the circle, and third one is called the circle itself. Now, this concept says how we know that a point is an exterior point or an interior point or a point on the circle. Suppose I am taking here 3 points P, Q, R. Now by looking this, we can say that P is an interior point, Q is an exterior point, and R is a point on the circle. But there is a geometrical condition behind it. What is that geometrical condition? Look here. Look to the figure. In the figure, if we join the point P with the center, then we get a line segment OP. Now, OP, the length of OP is less than R or less than radius. If the line joining the point with the center, its length is less than radius, then that point is known as an interior point of the circle. Now comes to the second point, that is Q. Q, if we join Q with center O, then OQ is greater than radius. As OQ is greater than radius, then Q is an exterior point of the circle. Now comes to the third point R. OR. Joining R with O, we get OR. It is clearly seen or visible that this is equal to radius. As OR is equal to radius, then R is a point on the circle. So we conclude that To find whether a point is an exterior point, interior point or a point on the circle, we have to join the points with the center. If the distance between the point and the center is less than radius, then it is a point, it is an interior point of the circle. If the distance between the point and the center is greater than radius, then it is a point on the exterior of the circle. If a point is on the circle, then the distance between the point and the center is equal to radius. That is the first concept which we will meet when we enter into the chapter. Now comes to the second concept. The second concept is, if we draw a circle with center O, consider a circle with center O, we draw three lines, three different lines. What are the possibilities? The three lines, among the three lines, one may not intersect or may not meet the circle, other may meet the circle at one point, the third one may intersect the circle at 2 points. So the first one is called a general line, general straight line. There is no specific name for that. That is a straight line which do not intersect or meet the circle. The second line, that is meet the circle at one point only. A line, a straight line which meet the circle at one point only is known as a tangent to the circle. That means this is a tangent of the circle. So then comes to the third line. The third line intersects the circle at 2 points. A line, if it intersects the circle at 2 points, then it is known as a secant of the circle. So here we meet three types of lines. One is a general line, there is no specific name for that. That line does not meet or intersect the circle at any point. Second line, which meets the circle at one point, that is called tangent of the circle or tangent to the circle. Third one, when the line intersects the circle at 2 points, it is called a secant of the circle. Now comes to the third one. See here, we will normally read about the tangent of a circle. This chapter specially relates to tangent of a circle. See here, B, look at the figure. B is a point in the interior of the circle. A is a point on the circle. We know that through a point we can draw infinite number of lines. That means through B we can draw infinite number of lines. And those lines, it is clearly visible that all the lines intersect the circle at 2 points. That means all the lines are secants. So there will be no tangent through a point lies in the interior of the circle. That means we reached at the conclusion that through an interior point of a circle, no tangent can be drawn. Now comes to the second point. A is a point on the circle. So as A is a point on the circle, see here we can draw infinite number of lines. Among the infinite number of lines, the line pointed as L meets the circle at one point. Meets the circle at one point, and other lines intersect the circle at 2 points. So we get only one tangent. That means we reached at the conclusion that through a point on the circle we can draw only one tangent. So as the circle contains infinite number of points, we can draw infinite number of tangents of a circle. So a circle has infinite number of tangents. Through a point in the interior of the circle, we can't draw or no tangent can be drawn. Through a point on the circle, only one tangent can be drawn. Now comes to the third concept. This is when a point is an interior point and when a point is a point on the circle. Now, if a point is an exterior point, so through an exterior point, from an exterior point, we can draw two tangents to the circle. Now, where the tangents meets the circle are called point of contact. So point B and C are called points of contact. Points of contact. So from an exterior point, two tangents can be drawn to a circle and we get 2 points of contact. Now the length of AC and AB, are called lengths of the tangents. Lengths of the tangents. So now let's recap it. What is a tangent? Now when a line meets the circle at one point only, that is called a tangent. Through an interior point of a circle, no tangent can be drawn. Through a point on the circle, only one tangent can be drawn, and a circle has infinite number of tangents. But from a point outside the circle, we can draw two tangents, and where the tangents meets are called points of contacts. The distance between the point of contact and that point is called length of the tangents. So AB and AC are called length of the tangents. These are the basic concepts. We will enter into the theorem part of the chapter, that is circle. So before going to theorem part, again I want to tell you one concept which relates to your theorem 10.1 of Ncert, that is the distance between a point and a line. From a point, what is the distance? Which distance is considered as the distance between the point and the line? See here, I am taking here a line L and a point P, not lying on the line. I want to find out the distance between P and L according to the theorem. See here, the perpendicular distance is the distance between the point and the line. Why the perpendicular distance? Because it is the shortest distance between the point and the line. As we know, if we take PQ, so that PRQ is a right triangle where PQ is the hypotenuse. Hypotenuse is always the longest side. Therefore, it is longer than PR. Like that, PS is also longer than PR or greater than PR. So PR is the shortest distance between the line L and the point P, which is the perpendicular distance between them. So the distance between a line and a point indicates or is the perpendicular distance between the point and the line. So this is the concept, what is the distance between a point and a line. Now comes to the theorem 10.1. The theorem 10.1 says that the tangent at any point of a circle, the tangent at any point of a circle is perpendicular to the radius at the point of contact. So I am taking here, look at this figure, I am taking here a tangent to a circle with center O at the point C. Means AB a tangent at the point C. So C is considered as the point of contact. That means if we join OC, we get the radius. So we have to prove that OC perpendicular to AB. To prove OC perpendicular to AB. Now, as we know that a line contains infinite number of points, in construction, take any point P and Q on line AB. Construction. Take any point P and Q on the tangent. Join OP and OQ. Join OP and OQ. Now comes to your proof part. Look at it, is very simple. As it is AB is a tangent at the point C, so other points lies outside the circle. Therefore, P and Q are exterior points of the circle. Exterior points of the circle. As they are exterior points, I told you the distance between the center is always greater than radius. That means OC is less than OP and OC is less than OQ, which implies that OC is the smallest distance between the point P and the line AB or the tangent AB, which implies that OC is perpendicular to AB. As OC is less than OP, OC is less than OQ, so OC is the smallest distance between the center and the tangent. So OC is perpendicular to AB. That means the radius is perpendicular to the tangent. So what we conclude? Now the tangent at any point on a circle is perpendicular to the radius at the point of contact. This is your theorem 10.1. Now comes to theorem 10.2. Theorem 10.2. We know that from an external point or from an exterior point of a circle, we can draw a maximum of two tangents. Two tangents can be drawn. So, your theorem 10.2 says that the tangents drawn from an external point of a circle are equal in length. The length of tangents drawn from an exterior point of a circle to the circle are equal with each other. That means here consider a circle with center O. Let A is an exterior point of a circle. We can draw two tangents AB and AC. AB and AC are two tangents drawn from the external point A. This is given. To prove AB is equal to AC, that means lengths of the tangents are equal. To prove. What to prove? Now AB is equal to AC. This we have to prove. Now construction. Join OB, OC and OA. Join it. Join OB, OC and OA. After joining OB, OC and OA, we get two triangles. One is OBA, other is OCA. So prove. In triangles OBA and OCA, OB is equal to OC. Why? Because this is radii of same circle. Radii of same circle. Then OA is equal to OA common. And as we read in theorem 10.1, that the radius is perpendicular to the tangent at the point of contact. That means angle OBA is equal to angle OCA is equal to 90 degree, because radius is perpendicular to the tangent. Radius is perpendicular to the tangent at point of contact. At point of contact. So in triangle OBA and OCA, we get OB is equal to OC, radii of same circle. OA is equal to OA, the common. OBA is equal to OCA, that is 90 degree. Radius is perpendicular to the tangent at the point of contact, which implies that triangle OBA congruent to triangle OCA by RHS congruency criteria. By RHS congruency criteria. As the two triangles congruent, then their corresponding parts are equal with each other. That means OA, that means OB is equal to OC, that is given. So you have AB is equal to AC. Implies that AB is equal to AC by CPCT. So we conclude that the tangents drawn from an external point of a circle to the circle are equal with each other. The length of the tangents drawn are equal with each other. Now, if you think it, now think, this is the theorem given, but what corollary is? Corollary means the rule which extract from the theorem. How easily we can prove a deduction? We can draw from corollaries from the theorem. So here you can also say that the line joining the center with the point from where the tangents run bisect the angle between the tangent. That means OA bisects BAC. So OAB is also equal to OAC. That means this angle is equal to this angle, as the two triangles congruent with each other. Again, it also bisects the angle between the two radii. That means it bisects OA, the line joining the center with the point where the tangents drawn, it bisects the angle between the two radii. That is, it bisects the angle BOC. So BOA is equal to your COA. That means from this theorem also we conclude the two corollaries. What are the two corollaries? Now the line joining the center with the point from where the tangents drawn to the circle bisects the angle inclined by the tangents, and it also bisects the angle between the radius of the circle, the two radii of the circle. That means OAC is equal to OAB, BOA is equal to COA. So this is all about your theorems and concepts relates to your chapter. So in my next session, I will discuss some important problems, possible problems which may come in your exam or frequently coming in your exams, like that proofs, deductions and any problems relates to the tangents. So be in connect with me. Comment, share and subscribe to touch with me for the success of yours. Thank you.